the exam. There are still a handful of people who have not taken it yet, so no conversations about it, please, as you sign to on the front of the exam. And then, so probably Friday or Saturday, I'll have results back from scanning and compiled so you can see how you did. And then when we get back, we'll talk about the exam content, and you can come into the office and see exactly what you missed. But we'll talk about like the most frequently missed items the Tuesday when we get back. Also the Tuesday when we get back, so there's some people have dropped. So you have an opportunity to maybe switch seats, and then we're going to say, is it the what? How many rows? 3?
So we're going to try to make it so that nobody else is not here anymore. So
3.
if possible, we're going to make it so that everyone's here.
Right, so there's that aisle.
Use this aisle here.
Yeah, there's the aisle there. So coming back on Tuesday, we're going to ask everyone who's used to sitting in the back, find a new home in front of where Morgan is. That would be also an opportunity for those in the front if you want to make an adjustment, but I hope there's not a lot of those, okay? So we don't want to make a whole new chart, we just want to revise it.
So if you're really unhappy that way.
Yeah, if you need a new spot to sit, then switch. Not now, okay? So Tuesday when we come back. Okay, so let's recap. I was going to show you the slide last time, but the conversation just kind of organically morphed into it. So let's just review it. So we talked about this is our what? This is a function for what does this give us? Exact or approximate, first of all? Does this function give us exact accumulation or exact rate of change? This is exact accumulation, and then so is it net or total accumulation? This is our exact net accumulation function, right? It's tracking the amount of change since x equals a, the amount of change in our quantity since x equals a. Okay, that's what that's doing. It's doing it by accumulating the changes little bit at a time, right? According to the rate function. And we saw we need that different variable t because we need a different variable to represent all the x values starting at a up to x. X is the right side of this interval of x that we've currentent accumulated up to, right? And so we need t then to go through all the completed intervals. We think about all the completed intervals and a current interval.
Yeah, if anybody, if
recitation?
Recitation, yeah.
So yeah, let's do recitation. Go ahead and pass that in.
Yeah.
And whenever you see an integral function like this, what are you thinking about? What are you thinking that represents? Remember? Okay, sum of changes in y, right? And where do we get that from? The long equation, right? The long A equation, right? Okay, let's get it. Everyone got their homework in? Any more homework coming in? Remember, when you see that, the net accumulation function, you think, oh, this is that long thing we worked hard on, where we summed up all the accumulation from completed intervals, plus a little bit for the partial interval, but with one qualification. What was the qualification?
Very small intervals.
For very small intervals. So it's that long A equation. It's essentially the same thing as that long A equation for very small intervals. And this is just a compact form for writing that. Okay? Is this an open form expression on the right or closed?
Okay.
Okay, we talked about last time. This is the idea of an open form expression. It reflects a process, right? This process of this summing up of a gazillion little changes in the quantity. So it doesn't involve a formula by which values can be easily computed. So we saw that if we put that into GC, it's got an algorithm to give us the value for a particular x. but we can't do it the way we could do x squared plus square root of x, right? So it's more of a conceptual kind of expression, as opposed to closed form. Closed form involves elementary expressions. These are the ones you've been used to your whole math career. Polynomials, trig functions, exponential. And these can readily generate values of the dependent variables, right? So they're computable, and oftentimes with pencil and paper, right? And so this includes nearly all the functions you've ever encountered, and they're practical, right? So advantage to this net accumulation is that the advantage is it's reflective of this process. We look at it and it reminds us of what we were doing, summing up a bunch of little changes in the quantity. But the disadvantage is, what is a sub f of 3? What is the value? It's not at our fingertips, right? Like in a closed form expression it would be. We'd have to put that into some technology like GC to find out what a sub f of 3 is. Okay? So we kind of completed the journey, but we kind of didn't, right? So we were able to come up with net accumulation and total accumulation if we had some accumulation at x equals a. But there would be another step to this. Could we get a closed form expression for this net accumulation function? So could we somehow, instead of expressing it this way in open form, could we come up, given the rate function, given the value of a, could we come up with a closed form? So, well, as far as what we've done so far, we don't know how to do that. Okay, so that's kind of just a review of a little bit of what we talked about last time, because we're going to use this language a lot now, open versus closed form. So, are there any questions about that? This is going to be a theme, all right? This is going to be a theme in what we're doing coming up. And so, the next thing. So, is this the journey we've been on? We know how fast something is changing at every moment. We want to know how much of it we have at every moment. So that was this. We derived accumulation given rate of change, right? So today we're going to start the reverse process. The reverse process, we said all calculus is about 2 ideas. So today we're going to start the other one. What? You know how much of a quantity you have at any moment, and you want to know how fast it's changing at every moment. That would be rate of change from accumulation. Okay, so let's summarize where we've been going. So we investigated a process for tackling the question. You know how fast a quantity changes every moment. You want to know how much of it you have at every moment. Okay, that's what we've been doing. But the accumulation functions we are now able to write are all represented in open form. Integral function form is an open form, which is non-computable, representing process, conceptual. So now we embark on the reverse process. Which is that? You can read it. And so now, actually, this reverse process now will achieve 2 things for us. The first thing it will achieve is just what it says. All right. So basically, if you knew how much of a quantity you had at every moment, by the end of this reverse process, we'll be able to come up with how fast it's changing at every moment. So just at face value, that has we can do that. But this will also achieve a secondary goal. Going through this reverse process will achieve a secondary goal, and then it will open the door to obtain our accumulation functions represented in closed form. This thing that we're not able to do yet, right? So those integral functions that are representing an accumulated amount in open form, by going through this reverse process, we'll find that we'll gain the ability to write those open form integral functions in closed form. Doesn't make sense. Blank stares. Is it? So anybody have a question on that? So the reverse process, so what we've been doing for the last month, now we're going to reverse that process. And what happens as a kind of, as a consequence of that, we'll be able to now go back to our integral functions and say, oh, now we can find closed form representations for those integral functions that we couldn't before. Okay? So the reverse process. So here's what we did, right? Everyone, yeah? I told you it was on the test, so those who haven't taken it versus those who have. Did you get it right? Exact rate of change, approximate rate of change, approximate accumulation, exact accumulation. And so then, having gone through that process, we said that we've earned the right, we've done the heavy lifting, we've earned the right to, we can just write the exact accumulation function down given exact rate of change. That should be like R sub f, right? So R sub f and R sub f of t over here. So now what we're going to do is backwards, right? So we'll start with, we know how much a quantity is changing at every moment. From that, we're going to build approximate accumulation, approximate rate of change. Finally, exact rate of change, which would be like R sub f again, R sub f, okay? And then, like before, having done the hard work, we'll be able to write exact rate of change functions directly from exact accumulation functions. Okay. All right, so here is the area of a square function. Area of a square function, and so f of x equals x squared. So what does x represent? What does x represent? Yeah, it'll be the length of the side, right? We all know the formula for the area of a square is the length of the side squared. So here's that function form, okay? And so whenever you come to a function like this in the past, you've seen this as what we call an amount function. An amount function, okay? You put in side length equals 8. This function tells you the amount of area for that side length. So you just choose different values of side length, and then the dependent variable would just give you amount. But now we have a new way of thinking about that. So that is a valid way to think about that. Plug in a side length, it cranks out the area. But we have a new way of thinking about this now. How is it we could think about this instead, based on what we've been doing? Instead of, boom, x equals 8, and the area is 64, the amount is 64, what's another way to think about that? Yeah.
To illustrate the drawing of a shrinking square on the graph.
Okay, but so for instance, so side length is 8. In the example, yeah, so you're on the right track.
Then you would have a line you would have a square with side lengths of 8, and the lines that you can see, which would be this line on top and the line to the right, would be at 8.
Okay, so that's really, you're back talking about amount. When it's 8, you get an area of 64. But how else could we think about that 64 coming about? You saw you first, yeah.
For each change in your side length, the corresponding change in your area is that amount squared.
Okay, yeah, so we can think, what were we going to say?
So your 64 is correlated to your y value, basically.
Okay, so, okay, yeah.
The rate of change in the area of the square is proportional to its side length squared. So if you change it in side length squared.
Okay, so yeah, so everything you guys are saying is true, but what I'm asking about is that value of 64, rather than it just being like, here's the side of 8, and the area is 64. What's another way now we can think about that value of 64? That's what I'm getting at. That it came to be. How did the area of 64 come to be? That's what I'm getting at.
The accumulation.
Yeah, so that you think of that any given area of a square accumulated from nothing, right? So we can think of this not only as an amount function, plug in 8, you get 64, but you can think of it as an accumulation function. That a square started from side length 0. As the side length grew to 8, the area grew to 64 in little bits, right? In little bits. So all these amount functions that you're used to, now we can think about as an accumulation function. So if it's an accumulation function, how can we write it? How can we write f of x then if it's an accumulation function? How can we express it? He said the integral of a rate function, but we don't know the rate function. Exactly, right? So if it's an accumulation function, we can write it as an integral from 0 to x. That's our side length, right? Growing from 0 to x. But it would, so that area would be growing at some rate, which we don't know what it is. But because we can think of that area as accumulating up to whatever area we get when the side length is x, we can write it as this integral function. And so our new goal will be just what is the rate? What is the rate? What was the rate of change as that square grew to side of to an area of x squared? Okay, makes sense? Okay, so here is that function x squared, and we're thinking of it as an exact accumulation function. And is it net accumulation or total accumulation? Is it net or total accumulation? I heard net and I heard total, but I didn't hear the right answer yet. It's both. It's both, right? Because the quantity of area starts at 0, you can think of it either way. You can think of it as the total area accumulated of the square, or the amount of change because it started at 0. So it's either. It could be both, right? It could be it's net or total because the initial value of area is 0. Okay, that's at x equals 0. Okay, so what we've got exact accumulation, whether we're saying that's net or total, doesn't matter. So in the process now, we want to come up with approximate accumulation in the hopes of moving towards rate of change. So what kind of function pretends to be an exact accumulation or amount function, but has constant rates of change? So let's do the same approach as before, but going backwards. Got exact accumulation, so we need to have a function that pretends to be like this one, but with constant rates of change. So can you imagine, and maybe sketch it in your notes. Sketch in your notes what you imagine to be a function trying to be like that one, but with constant rates of change. This one is, the rate is continually changing, right? So what would that look like? What would that look like? Think about that. Sketch it in your notes. What do you think an approximate function to that would be with constant rates of change? Okay, did you draw this? Did you draw this? Oh, people are shaking their head. You didn't draw that. Let's talk about this. Does this work?
No.
Oh, okay, cool. Why not? So you shook your head. Yeah. Okay. So good. So she's saying each of those steps would give a constant area, right? Because our y-axis now is not rate of change. Our y-axis now is amount of accumulation or amount. So a constant, like one of those blue constants, is going to give us what? A constant amount or a non-changing accumulation. So what would the rate of change on one of those steps be?
That's 0.
Oh, that's not what I wanted. Okay, here we were. So then, say this one right here. So that doesn't represent a constant rate of change. It represents a constant area. What is the rate of change for that then?
0.
0. And what's the rate of change down here for this constant area?
0.
0. So this way of approximating this is basically just giving us a rate of change of 0 everywhere. And like many of you shook your head when you saw this, you said, no, this will not give us, this is not the way to try to approximate that with constant rates. Why? This is approximating them with constant areas so that you just, rate of change just 0 everywhere. Okay, good. But, okay, so why do I bring that up? Because our experience in many, many semesters of doing this is the way that students try to draw an approximate accumulation function from an exact accumulation function. Because we're so used to doing this on the rate of change functions, right? It's not the same now. It's not the same. This step function will give constant, what, amounts of accumulation or 0 rate of change. Don't do that. Don't do that. So what instead? What instead is going to work? Yeah.
Depending on how many moments you'll have different segments instead of a curved line.
Okay, so he's talking about moments, within moments. So within a moment, you're going to have
A straight line instead of curved.
right. So straight line segments within moments, trying to be like that red curve, right? Straight line segments within moments, trying to be like that red curve. Okay, and we want to use, yeah. So what we call it, piecewise linear, right? And that's what our approximate accumulation was before too. It was piecewise linear. In every moment, we had a linear piece, and they were joined together, right? Okay, so how can we construct that? What is going to be the way that we construct that? So we're going to use information from the exact accumulation function to construct a piecewise linear graph. So we're going to use actual values of accumulation, and then we'll join those how? We'll join those correspondence points with linear pieces. Okay, so we want line segments whose endpoints are on the curve. Right? Line segments whose endpoints are on the curve. So since we're building it from this approximate accumulation function, it's gonna start with using individual correspondence points from that. So here's an example of one with what? How big are the moments here? 1. So here's with moments of length 1. And so what did I do? For the first moment, we said, okay, what's the actual amount of accumulation, the exact at the start, at the end of the moment? And where do we get those? We get those from the exact function we're given. And then we can build the equation of that line between those 2 points. And that is trying to be like the exact accumulation function curve, but with a constant rate, right? Constant rate of change. Same with this. Okay, so constant rate of change. Constant rate of change on an accumulation function looks like linear pieces, right? Linear pieces. Okay, so then to make it better. Oh, by the way, so what I didn't mention about the reverse process, it's going to go a whole lot faster because we've built lots and lots of tools in the forward process that we can use. So it's going to go a lot faster, okay? So look we're already talking about smaller intervals. With smaller intervals, what's my moment size now? A half. And how's the approximation now for that compared to before? Yeah, so this you can see that it deviates, not a lot, but quite, a significant amount. As soon as you make those moments half as big, now these line segments are hugging that curve a lot better. So this is pretty decent approximation now. Again, constant rates of change over each interval are represented by a line. Okay, so that function, so with these moments of 0.5, this is a piecewise linear graph. We're going to apply what we learned before, and we're going to build it. You're going to build it. You can do it. Okay? So we are building from, where's that thing? We're building that from, what? Information in this graph, right? The way that we're coming up with the approximate accumulation is from the exact accumulation. Specifically, what information are we taking from the exact accumulation to get this? Is everyone on their laptops taking notes? Okay. So what specifically with these moments of 0.5, what specifically from the exact accumulation function, what information are we taking to build the approximate? The point, which points? Yep.
The endpoints of each straight line.
Yeah. Right, the endpoints of the moments. So notice, at the endpoints of the moments, we have a common correspondence point between exact and approximate accumulation. So that's what we're taking from the exact accumulation to build approximate. So first hint, those correspondence points are going to be crucial, right? These are what you're using to build that thing, the approximate accumulation. All right, what will the function look like? Just in the big picture, what will we be writing in general here? What kind of thing? Remember doing this before? Coming from the other way, right? So we did the same thing, but coming from knowing the constant rates. Now we don't know the constant rates. Instead, what do we know? We know some particular correspondence points of exact accumulation. From those, we're going to build the same type of function that we built before. And that'll be our approximate accumulation function. Again, capital A, but coming from the other way, right? Coming from exact accumulation. So, this will be what? Piecewise linear. First piece will be x from what to what? 0 to 1.5. 0.5, sorry. Next piece will be 0.5 to 1, etc. And what will be the structure of each of those rules that we write? So for each of those moments, we're going to have a rule. And what will be the big picture, the overall structure of each of those rules? Do you remember? Do you remember what we did? Just MDX?
Plus the previous accumulation.
Y initial, or yeah, everything accumulated. Y initial plus change in Y, which we express as MDX, okay? So, yes, right. The structure of each one of those is going to be, so, like, area initial plus change in area. And the change in area will be as M change in X. I really should, so delta X is 0.5. That's the parameter, so I should really be putting dx here. Dx changes, right? It's a changing value through the moment, right? Delta X is set at 0.5. It's a parameter. Dx will increase through the interval, right? Will be a changing amount of change in a current interval. All right, let's take 10 minutes and see how we do. Can you do it? Those correspondence points, we have the values from the function, right? We can calculate each of these individual rates. What is this rate right here? Call it M1. What is the value? 0.5. Change in area over change in X, right? And you have the values of those endpoints to do that. So you got a constant rate of 0.5. Next interval. So let's actually do the one from the next interval. What is this correspondence point right here? That's the point 0.5 and 0.25. Right? X and corresponding area. And then this one up here? 1 and 1. So we want the constant rate of change, right? That gets the same change in area for this moment. We want the same change in area, same y change for this particular moment. And we do that by, so that's M2. M2 is, that's blue now. Change in y, change in area over change in x, which turned out to be 1.5. So here's M2. M2 is 1.5, etc. So we can keep going that way. We've got the values at the correspondence points from the exact area function, and we can get those constant rates. Okay, that's just part of the battle here. But we know that's what these are going to be in each line. Okay, so now going back to this picture, we've seen it lots of times before. Not sticking with a lot of us, right? With a lot of us, it's just not sticking. That x is a variable. Lots of you, I saw, you came up with expressions that just gave you a number. X varies through intervals. So for any given interval, I'm showing the third interval, x is going to what? X is going to be what? It's going to start at 1 and it's going to vary to 1.5. We want all areas, approximate areas, for all those x values. So we pick a basic one and we say, what is dx? If we're starting at x equals 1, what's dx to any arbitrary x in that interval? Dx is x final minus x initial. That would be in the third interval. This would be the change in x in the third interval. This right here is what a lot of you are still not grasping. It's really important. X varies through the interval, and dx is how much it's gone into that interval. So it's going to be x final, an arbitrary x, any x, every x, minus the starting x, 1. Do you see that dx is x minus 1 in the third interval? Thinking of x as varying through that interval. Okay? What's the corresponding change in x in that interval? So that would be represented by this. So this is x minus 1. What's the corresponding change in x? Sorry, change in y, change in area. dy equals m dx. And dx is x minus 1. It should just feel slightly familiar. Maybe just like an inkling from your past, right? I'm being sarcastic. Okay. So m dx. What is the value of m in this interval? Was this 2.5? So the same way we did the other ones, take change in y from here to here. So that's from here to here. The change in y over the change in x was 2.5. So that is our slope in the third rate of change in the third interval. And then what is the initial area in that interval? So you could write it as a value. What? It's 1 squared. Or you could write it as a of 1 that we got from the last interval. So I could write a of 1, which comes from the previous interval. All the accumulated area in the previous intervals would be a of 1. And in this case, it happens to be the value 1 also. So initial area plus the change in area, which is rate times the change in x. 2.5 times x minus 1. Now that's a function. That's a function. Plug in any x between 1 and 1.5 and it tells you the approximate accumulated area. Just a plain number won't do. We need to get every single approximated area in that interval, given any x. So if I plug in 1.4, the change in x will be 0.4 times the current rate, gives me the change in area, plus all the accumulated area before. And that would tell me what the accumulation is at 1.4. Can you finish it now? Can you finish it now? So either way, you could, for the initial areas in each interval, you could use the function notation the way that we've done it here. We can pick it off from everything accumulated from before. Or you can write the value. You know the values based on the exact function that you started with. Okay, so hoping, praying, admonishing, saying, if we didn't get it today, can we get it from here on? Can we get this from here on? Any questions on that? Doesn't make sense. So if you haven't finished it already, so finish it on your own. Finish it on your own, okay? Last chance, questions. Please ask if I lost you. Okay, so part of homework for Tuesday when we come back will be to write that whole thing. Write that whole thing. Okay, so what about any f, not just x squared? So we were dealing with an exact accumulation function, x squared. What about any accumulation function? And instead of just like before, instead of writing it in lots of different pieces, can we write it in one rule? Can we write it in one rule? Yes, we can. We have the tools to do it. So let's just start with some review. What kind of function is displayed by the red graph, the curve f? What kind of function is that? Exact net accumulation. For sure it's net accumulation and maybe total, right? For sure it's net accumulation because it starts from 0. What function is displayed by the blue graph? It's our approximate accumulation, right? Approximate accumulation using constant rates to try to mimic that exact accumulation function. Okay? So now, we're going to do what we just did, but very generically now. F could be any function, and then the current interval could be any interval. So I'm going to show it in the second interval. I'm showing the current value of x, but that could be any interval. That could be the 4th interval. That could be the 8th interval. That could be the 100th interval. It's not necessarily the second interval. It's just the way that I made the picture to make it nice and big and clear. Okay? But that x could be in any interval, any moment. All right, and so how are we going to... We're going to express the constant rate as change in y over change in x. Where are we going to get our y and our x values for that? Where are we going to get our y and x values to get that constant rate in that interval? Then they're going to come from f, right? They're going to come from f. So they have to be the endpoints of that interval. Those are the common points between exact and approximate accumulation. So we're going to pick off the values of exact accumulation from the endpoints and let those also be on our accumulation function, approximate, and then make the constant rate between them. Okay, so the approximate rate function will be of this form, right? It'll have the form change in y over change in x. So we're gonna write that first, okay? We're gonna write that first. We're going to write this approximate rate function in one line, not as a bunch of individual pieces, kind of like what we did before. We need to write it in one line. So what do we need to do that? Like we just said, there's a change in x. There's the corresponding change in y. Is this the second interval? Could be any interval. Could be any interval. Okay? So if you can write an expression for this, generic for any interval, then you're writing the approximate rate function. if you can write an expression, this expression, considering this to be any interval, then you are essentially writing the whole approximate rate function. What do we need to do that? What do we need to do that to write? So, but generically, to get change in y, we're going to need I'll do one more thing, and then I'm going to put you up. Okay, so change in y is going to be calculated by y2, or yeah, y final minus y initial. And what about change in x? Okay? Here's our current value of x. It could be in any interval. We need to then write this in terms of x. All right, so here's the key. I'll go back to it in a second. The key is getting these coordinates of these 2 points, right? These points are going to be what we build that constant rate with, but getting those coordinates in terms of x, which is somewhere in the middle of the intervals. It's increasing through the interval. So given a value x in any interval, and it could be any x in that interval, how do we get the coordinates of that point? And then how would we get the coordinates of that point? So we're going to draw on something that we've learned before. Go. Lots of you are using x comma f of x. I plotted that point, x comma f of x. And the question is that correspondence point, are we using that to find the constant rate of change in that interval? No, so which points are we using? We're not using x f of x. You see where it is on the curve? It's not part of getting that constant rate. What points do we use? This point and this point, the end of the interval. And the key to this is remembering the tool that we had to get the x value at the start of any interval. The x value at the start of the interval that x is in. That's the key. Once you get that first x value, then the rest kind of falls out. What is the x value at the start of the current interval? That's what we're trying to conjure. The x value at the start of any current interval. Did you get it? Very good. What is the denominator? Okay, so we're good. Good. Okay, so the coordinates of that first point, many of you are starting to discover it, are left of x and f of left of x. Where left of x is this very helpful, this very important function that we have that takes whatever x you're at in the current interval and spits back the x value at the start of the interval. So if x is anywhere in this interval, left of x will be this right here. Right? If x is anywhere in that interval, left of x is exactly what we need, the starting x value of that interval. And then we got the y value. Okay, so now what's the x value at the end of the interval? So how would we get from left of x to here? You add delta x, right? You go over further by delta x. So that's the x coordinate of that point. and its corresponding y coordinate. So the idea of left of x is now it'll give us this constant rate when x is in any interval, right? Because that's how left of x works. It always gives you the starting x value at the current interval, wherever x is. So as x moves through these intervals, it will continue to update the constant rate. So the approximate rate function is this: change in y over change in x. So now this allows us to build what A is, but I'm going to leave that to you. Leave that to you. So what we did on the previous screen, we wrote AX in many lines, right? We did what? Y initial plus the change in y. We did it for each individual moment. Now we can do it in one line. We can write AX in one line now that we have the constant rate function. Okay, be safe over break. Have a good time. Check Blackboard for homework.